Act 0. Yeah, that's probably 3D.
Now, I've been working with 3D models and animation for some years now, and I have to say, rendering, actually pretty easy.
Today we have all kinds of game engines and software that make the process of creating and displaying 3D models a breeze. But it wasn't always this way. Back in 1992, the world looked a fair bit different. George Washington was the Canadian Prime Minister, and dinosaurs roamed the Earth.
Yeah, I wasn't alive yet, so who's to say what was what?
id Software had just released a revolutionary game, Wolfenstein 3D, which was loved by gamers, critics, and raptors alike. So what did this monumental achievement look like?
Oh! Does this count as clickbait?
But seriously, the architecture behind this game is fascinating. See, despite looking 3D, the world and all its physics are actually 2D, and the graphics engine is just working really hard to fake it using an algorithm called Raycasting. See, the hardware at the time was just not powerful enough to support true 3D, so this form of fake 3D was necessary to circumvent the limitations of that hardware. After all, we had to give those hamsters a break at some point. But as time progressed and hardware improved to the point of supporting true 3D, raycasting mostly got lost in the sands of time. Which is a shame, since I still think the raycasting algorithm has a lot of potential outside of simply being a cheaper way to render 3D. Sure, it's highly limited, but if you embrace those limitations, you'll find there's actually a lot of things raycasting can achieve that traditional rendering can't do, or at least not as well. So today, I want to reanimate the technique using the Godot game engine to see just what a modern raycaster could look like. Let's get started. Act 1. Raycasting Fury. So originally I planned to demonstrate raycasting using a laser pointer and some colored pencils.
Green. Green.
But that was both slow and ineffective.
Maybe I shouldn't use a colored laser.
Also, it turns out lasers are kind of dangerous, so be careful. Instead, let's use an animation. We'll start by defining a grid world, or better known as in Godot, a tile map. The camera is positioned somewhere in this world, with a view cone that defines what the camera can see. Every frame will cast a ray from the camera until it strikes a solid wall. Using the length of the ray to determine distance, as well as the wall's texture, we can then render the corresponding column. Repeat for every column in the width of the canvas, and voila! 3D. Seems easy enough, right? But what's the catch? The catch is the ray stepping itself. A naive approach would be to choose a constant step distance. However, choose one too large and the precision is very low and the corners may be stepped over altogether. Choose one too small, and you get the world's worst game of connect a dot. Not to mention all the redundant collision checks. Instead, I opted to design a more complicated algorithm, or as we programmers like to say, sophisticated. Now for the record, I'm not claiming I invented and or own this algorithm. I merely designed it myself without use of a guide, so for the purposes of this video, I will claim this is my algorithm. If that doesn't work for you, I don't know, sue me.
Damn it.
The motivation behind this algorithm is instead of using a constant step distance, we step exactly the amount required to reach the next cell. Not only does this give us maximum precision, it also guarantees we are performing the minimum number of collision checks. Although, this is a bit trickier to figure out, since we are now using a dynamic step distance instead of a constant one, but it's nothing a little math can't solve. Alright, so let's break down the problem into a single cell. Given a point somewhere within the cell, we need to shoot a ray to intersect one of the 4 edges. For directions lined to the basis, this intersection point is trivial. For example, the intersection for the up direction is the point's x position, and the top edge is y position. For non-basis directions, things get a little trickier, so let's consider the cases. We'll start by calculating the intersection with the horizontal edges. Based on whether the ray is traveling up or down, we can determine which edge the ray can intersect with. Of course, this intersection may fall outside the cell, but no biggie. In that case, we'll simply need to calculate the intersection with the corresponding vertical edge. Edge intersections boil down to the classic y equals mx plus b equation of a line, where m is the slope and b is the initial value. Slope is easily calculated from the direction, rise over run, and the initial can be obtained from some simple rearrangement of the equation. For vertical lines, we can also rearrange the equation, this time to be in terms of x. However, it turns out this is in fact not how math works, and the rearrangement actually looks like this. In my defense, it was like 2 AM when I devised this algorithm, so some new math mistakes were inevitable.
I think I found the problem.
After we have the intersection point, we'll check it against a max distance to prevent our rays from shooting off into infinity. Next, we'll check for a wall tile, and if found, we draw a line using the tile's color and distance. Don't stress over the distance code at this point because it's wrong. To render every column for the viewport, we simply iterate with x pixels and lerp, short for linear interpolate, for a field of view. And that's actually everything. Giving it our first run and we get something that resembles walls? Like I mentioned before, the distance code is less than accurate, so after consulting a raycasting tutorial, hey, editor Ryan here. I just wanted to clarify that one I said earlier. Now for the record, I'm not claiming I invented and or own this algorithm. I merely designed it myself without use of a guide, so for the purposes of this video, I will claim this is my algorithm. I was only referring to the cell-step algorithm and not the entire project. I did need to consult numerous tutorials throughout the process since, well, I'm not perfect. Alright, back to the video. The distance code now looks like this. Honestly, I still don't fully understand why this works, but hey, you can't argue with the results. Another notable problem is this fisheye effect. Again, Raycast tutorial to the rescue in this one. The problem is that our distance code uses the length of the ray, so if we're facing the wall, then rays at the ends of the field of view are noticeably longer and the column renders shorter. The fix is everyone's favorite Sakatoa. Actually, I'm not sure if anyone actually liked using these triangles in school, but trust me when I say this, trigonometry is probably the single most useful math skill in the real world, or virtual in this case. To fix our distance code, you may notice that our ray vector is the hypotenuse. You may notice that our ray vector is the hypotenuse to a triangle. So using cosine with our angle, we can obtain the actual distance to the wall. We don't even need the absolute value of the angle since cosine is symmetric, i.e. positive and negative angles yield the same result. And with that, we've got a functional, albeit bare bones, Raycaster. Performance-wise, I can achieve a smooth 60 FPS at the default window size, but upscaling proves this code does not scale very well. And the performance will only decrease as our Raycast code gets more complicated. Sophisticated. The issue is we are using single threading, so every column is computed one after another. Although columns have no overlap, so there's no reason why we can't simply run them all at the same time, or to use the visual term, in parallel. Thankfully for us, we have access to some hardware that is very efficient at parallel computations involving graphics. No hamsters required. Act 2. Enter Compute Shader. So what exactly is a compute shader? Well, shader is just a fancier word for code that runs on the GPU. So compute shader is basically arbitrary code that runs on the GPU. But what would entice one to use the graphics processor to execute code when we have a perfectly suitable central processor? In short, parallelism. See, where your average CPU has, say, 8 cores, your GPU has thousands. Therefore, if your code has a lot of independent tasks, such as processing an array for every pixel in the screen width, you can achieve major performance benefits by executing in parallel on the GPU. Also, graphics card hardware is much more optimized for graphics-related calculations such as vector and matrix algebra. Honestly, for how useful GPUs are for general-purpose parallel tasks, maybe we should rename it to the Parallel Processing Unit.
What have I done?
Okay, so I had a draft of this section which went into detail about how Godot implements compute shaders, and it was both really dry and way too long, so I'm just gonna use an abridged version instead. If you still wish for a more detailed look, the source code for this project is available on GitHub, link in the description. I'll also link some tutorials I used myself when learning about this stuff, since the documentation is, well, non-existent. I may even make my own tutorial on Godot for compute shaders, so let me know if you'd like to see that. Or don't, I guess, I mean, that's fine too. The first thing to understand about compute shaders is the roles of the GPU and CPU. The shader code itself is written in GLSL, executed on the GPU, and dispatch code written in GDScript, executed by the engine by the CPU. The second thing to understand about compute shaders is the two types of thread groupings: work groups and invocations. The major difference between them is that invocations are statically defined in the shader and cannot change, whereas work groups are dispatched from the dispatcher and can be defined dynamically. Each are additionally organized into a 3D vector x, y, z. So for example, I could have xx, I could have 8x and 8y invocations for a total of 64. Then in the shader I could access a pixel in the texture using the xy ID, and I would guarantee that only that thread would access that pixel. In the Raycast shader, we only need to run columns in parallel, so we'll just use one dimension. I've also heard/read multiples of 64 are optimal for hardware reasons, so we'll use 64x invocations. On the CPU side, we'll divide the canvas size by 64, the number of invocations, to calculate the number of workgroups we'll need. Also note integer division is important here, since we don't want to end up with more threads than we have columns, else the shader will try to read pixels that don't exist. Now converting the actual Raycast algorithm to shader code was no easy feat. See, shaders often lack good debugging tools, and they have this really neat feature, where small errors end up breaking reality.
What? No. No! Actually, that one's better. Oh, it was just a dream. Oh, that was awful. I dreamt about the Star Wars prequels.
Okay, in actuality I didn't break reality that hard, but it's not exactly what I would call correct either. Honestly, the conversion process was kind of a fun test of my understanding of low-level programming concepts. Perhaps like a game show. It's time for Spot That Bug! Today's contestant is wearing an eye patch, but I cannot confirm if he's a pirate. Alright, your first prompt is...
Caterpillar. Spider. Butterfly. Oh, floating point error.
Yeah, I actually want to bring special attention to this specific one as it's pretty interesting. Here's the scenario. I am not moving the camera anyway, yet the walls are doing this glitching effect. This tells us that despite providing the same input to the shader each frame, the results are somehow different. This is what is known in the programming world as undefined behavior, and there aren't too many sources for it. The first one that came to my mind was floating point error. See, decimals are tricky in computers, so a floating point number won't always be exact. It may be close enough but not truly exact. But repeated mathematical operations utilizing floating point numbers can quickly accumulate more and more error, to the point of being noticeable. Case in point. See, in my Raycast code, I'm adding the distance from every step. Since the distance calculation involves a square root operation, the error is relatively high. Not so high that it's noticeable, but adding up the distances results in the final value being slightly different frame by frame, even with the same initial conditions. The solution is to cache the starting position and calculate the full distance every time. This is no slower than the other method, and it removes that pesky precision error. Now that everything is back to what it was before, how much more performant is our compute shader? Let's circle back on that later. Before that, I want to cover some other topics. First to note is the minimap. Interestingly, this is actually what the world would look like if Godot were to render it itself. This was achieved using a sub-viewport with its own camera. The player also has this vision cone which is scaled perfectly to match the field of view and far plane the Raycaster uses. Adding in some light occlusion to the maze tiles, the resulting view cone shows precisely what is being rendered on the canvas. Not only is this good for debugging, it's also a nice aesthetic. Next up is texturing. To sample a pixel from a texture, we only need one thing, the UV coordinates. Oh, and the texture itself, I guess. Basically, it's just XY coordinates of the pixel with a different name as to not be confusing. However, they are mapped to the range 0 to 1, so the top left corner is 0.0, and the bottom right corner is 1.0. Unfortunately, UV unwrapping, as it's called, is normally one of the most frustrating and time-consuming processes of 3D modeling. Heck, I'm not even good at regular wrapping. But fortunately, all of our walls are just basic squares, so unwrapping isn't necessary. Since our walls are rendered per column, we can obtain the UV coordinate simply by lerping through the pixels, similar to obtaining the angle for raycasting. For the U coordinate, we need to know what part of the wall to restruct. Thankfully, we actually already have this information. If we know the coordinates of the cell of a ray struct, and the exact position of the ray, calculating the U coordinate is simple math. For testing purposes, I'm using this UV grid I generated in Blender. At first glance, everything looks great, until you start to move around. The issue is not immediately obvious, but if I zoom into this one wall, it's easier to understand. Here you can clearly see that the cells towards the edges of the screen are compressed compared to those in the center. After some digging, I finally found the culprit. Tan. No, like the trig function. See, the original lerp function simply lerps through the angles and supplies that to the raycast algorithm. However, if we consider how the angle maps to the x-coordinate, trigonometry tells us it's the tan of the angle. But that's the problem. Tan isn't linear. Graphing now, we see that tan is almost linear for angles close to 0, i.e. close to center screen. But as it gets far from 0, it deviates from linear very quickly. Result is that the samples with larger angles are more spread out, hence the warping effect. After many failed attempts at remedy, I realized the solution is more straightforward. If we need the samples to be evenly spaced, then just start there. We'll lerp for the x positions instead of the angle, which is from tan of field of view to tan of negative field of view. Then to obtain the actual angle from the position, we simply perform an arctan. And this makes total sense. If our textures are being warped based on a tan curve, then naturally the solution to counteract the warp is its inverse, arctan. And finally, everything looks great. Although I swear there's still a warping effect in walking closer to the wall, but I think that's just an optical illusion caused by textures being grids. Okay, now let's finally loop back to the performance evaluation. How much better does the project run now that it uses a compute shader? Yeah, it's somehow worse at 4K resolution. Now I know what you're thinking, aren't compute shaders supposed to be fast? How could it be slower? See, when working with parallel algorithms, you always have to consider the overhead of setting up and syncing threads. In this case, after rendering the final image, its data has to be copied from its raw binary form to create an image that the engine can actually render. For smaller resolution sizes, this really isn't an issue, but for large 4K images, this overhead is a massive bottleneck. To better illustrate this, consider an analogy. You want to travel between two cities pretty far away. Luckily for you, humans have invented a pretty fast method of travel. However, despite being pretty fast, there is a considerable amount of overhead on every step of the journey. You have to face long baggage check lines, understaffed security, ridiculous distances between terminals, unoptimized baggage claim, etc. In the end, you start to wonder if you're spending more time with the overhead stuff than actually traveling. Oh wait, I just perfectly described the airline industry. Yikes. You know, that would actually be pretty funny, if it wasn't so sad. Anyways, our issue is that although compute shaders are great at general parallel computations, we don't have a great way of interfacing directly with the graphics pipeline. And graphics shaders are great for, well, graphics, but their rigid pipeline structure makes more general calculations more difficult. The ultimate solution was to employ a hybrid approach. So first we used the compute shader as before, but instead of outputting the entire canvas, we only output the data required to perform the render. This is only defined for each column, which is significantly less than every single pixel. Finally, we pass that data to the graphics shader, which is used to actually render the image. So, why not? Act 2.9, Hybrid Shader. Modifying the compute shader is actually straightforward. We leave the code alone up until we would normally render the column, and just not do that. This ray hit struct has all the data we need, so we just simply write it to an output texture. And this may look kinda weird, but storing arbitrary data inside textures is a very common practice in shaders. We as humans may like to visualize textures as images, but by no means must they only store color data. As long as you tell the GPU how to interpret its contents, it really doesn't care. In the end, the output texture has 3 entries for every column. They store in some shape or form the array's distance, texture index, u-coordinate, position, and normal. We'll cover all these values in due time. In the graphics shader, our main task is to use the distance value to somehow determine what color the pixel should be. And unlike before, where we could simply render the entire column at once, our fragment shader works on a per pixel basis. So my idea was to use the distance to create a range so that 0.0 corresponds to the top of the wall, and 1.0 corresponds to the bottom. Then we apply the v-coordinate of the pixel, which is essentially its y position on the canvas, to this range to obtain a v-value. If this value is less than 0, then we draw the ceiling. If it's greater than 1, then we draw the floor. Anything in between is part of the wall, so we use this new v-value as the vertical texture coordinate when sampling the texture. The final equation looks like this. Honestly, I've recalculated and simplified this equation so many times, I myself don't really understand how it works anymore. But hey, the GPU thinks it works, so I guess I trust it. And yes, the scene does look significantly different. I'm kind of recording these clips out of order, but I will explain everything in due time. For now, let's reflect on the hybrid shader. Performance-wise, it's greatly improved. At full 4K, the app now runs at a smooth 60 FPS. Implementation-wise, I still feel a little iffy about it. Even though I was hyping up textures a bit ago, this approach seems a little on the hacky side. I mean, it works, but it's not the most elegant thing. The output texture is pretty unintuitive, and it's a fair number of wasted components.
I don't know, what do you think? Sir, this is a Wendy's?
Act 3. Pizzazz. Now that the base rendering algorithm is functional and efficient, we can start having some fun with texturing. First up, lighting. To perform lighting we need two components, the light and the surface normal. A normal vector is, frankly, an odd name to describe which direction a surface is facing. In our maze, the walls are the surfaces, and they can only face in one of four directions, so we can simply assign the normal vectors in a similar way to the u-coordinates in the compute shader. As for the light, there exist numerous types, such as directional, point, and spotlights. I did experiment with point lights for a while, but this solution didn't scale very well. I'm also going to rule out spotlights, since we saw how well the laser pointer went. Instead, I did what any sane person does when the going gets tough. Cheat. We'll simply light every wall as if there's a directional light angled in front of it. Realistically, this doesn't make a whole lot of physical sense, but, you know, cheating. The result is pretty underwhelming. Since all of our walls are flat, they will get lit evenly. A more advanced method is to supply the normal vectors per pixel instead of per surface. This concept is known as a normal map, so each of these pixels actually contains normal vectors, and we can sample it the same way we would sample diffuse texture to obtain pixel level normal vectors. Almost. The issue is that normal vectors are aligned to the z-axis, which, fun fact, is stored in the blue component of the image, hence the texture has a blue tint. In case you've ever laid awake at night wondering why it's blue. I know I have.
Oh, that's why.
See, none of our walls are in fact faced straight up, so we can't use the vector as is. Now this is where things get a little linear algebra, E. To convert our vectors into the correct space, we need a matrix called TBN, which stands for tangent, bitangent, and normal. The normal vector points away from the texture, whereas the tangent runs in the u direction and bitangent runs in the v direction. We already have the normal vector, and since all our walls are vertical, the bitangent is always straight down. For the tangent vector, we can actually take a linear algebra shortcut and use the cross operation to obtain the orthogonal vector. How does this work exactly?
Your guess is as good as mine.
After applying the matrix, the effect of normal mapping is very evident. Shadows and lighting are much more realistic for the texture and adds a very welcome layer of depth to the flat walls. Now originally I was going to end this act here, but then I watched this video on how Spider-Man and other modern titles use a technique called parallax mapping to imitate more complex geometry. A technique that makes something that's actually 2D look 3D. Nowhere ever heard that before. Although, full honesty, I had never actually heard of this technique, or had the slightest idea of how it actually works, so it's time to break out the old tutorial. This is also where I obtained the original brick texture you've been seeing. I did manage to implement normal mapping with the old texture, but parallax mapping was less than successful. But arguably I won in its own right, it's so shiny. Also, fun fact, my commit message for this step was attempt parallax mapping, which is quite fitting. See, the old texture wasn't really designed with parallax mapping in mind, so I wasn't sure if the issues were caused by my sketchy parallax map, or my code. Spoiler alert, it was the code. In the end, I swapped the tutorial texture so I could, actually get it to function. The parallax mapping technique is fairly hard to explain, but in short, it aims to offset the texture coordinates to better reflect the actual height of the surface as described by the parallax map. Make sense? Yeah, me neither. Honestly, I don't fully understand this implementation, however I do know the main component that we need is the view direction. This is why we need to export the ray position from the compute shader, and the view position can easily be obtained from the player. For the Z component, we can use the V texture coordinate for the wall position and 0.5 for the view position, as the camera is always at half the wall height. After all of that, the code still did not immediately work. So I literally just rearranged the matrix components, the order in which vectors and matrices are multiplied, and swapped minus signs until it finally functioned, for whatever reason. I think my big issue was that the TBN matrix was upside down, or backwards, or inside out. I don't know, it was wrong. But hey, it works now, and wow is it ever cool. Now instead of just lighting more realistically, the walls appear to have proper 3D geometry. The grout between bricks is actually sunk into the wall, and the bricks can render in front of other bricks. And remember, these walls are still flat, 2D walls in fact. But this clever technique can imitate what 3D geometry would look like. Now the technique is a little crude, so the illusion starts to break at tense angles, but that's easy enough to look past. All in all, pretty epic. Pizzazz? Check. Act 4. Finishing touches. At least for now. First on the list of finishing touches is optimizations. Most of which just include minimizing the amount of data being passed to the shaders. Not that interesting to mention in detail. Although if you're one of those nerds who spends their Friday night sifting for commit histories, I know I do. And all the changes made can be viewed there. With that said, there is one optimization worthy of mention. Since the compute shader creates the texture for the graphics shader to render with, it's possible to reuse that texture for more than one frame. I.e., if the physics don't change, then we can continue to use the old texture over and over. At first it seems a little pointless, but being able to re-render the frame without reperforming the raycast could be useful. For instance, if we ever decide to implement animated textures. To achieve this, we simply define a new signal in the player class. In the process update, if any of the physics change, in this case we care about velocity and angle, then we emit the signal. In the canvas script, we listen for the signal and only recompute the texture if it's fired. We also need to recompute it if the canvas size changes, as the size of the output texture changes as well. Visually, nothing has changed, but it's more optimal. The final task, at least for now, is to address the far plane issue. If I were to decrease the far plane distance, we can see the effect is less than pretty. If we transition from rendering walls to not rendering walls is, well, non-existent. The aesthetic solution is to implement fog in order to fade out gradually. Now fog may seem kind of complicated, but it's actually really simple. We only need to blend the pixel color with a fog color with increasing intensity the closer it is to the far plane. To achieve this, we implement a gradient texture. These are 1D textures that are very effective when a smooth transition between values is desired. The initial attempt is almost correct, although it does look a little off. The main issue is that the floor and ceiling are not being affected by the fog. Remember, these are drawn as solid colors and don't currently have a concept of distance. However, using the pixel's v-coordinates, we can actually perform a reverse distance lookup, and the result is pretty effective. Hopefully I can leverage this form of reverse distance calculation to implement floor and ceiling textures in the future, although that's a rabbit hole for another day. It's also possible to change the fog color if the white was too blinding. All in all, awesome stuff. Epilogue. And that just about wraps things up. I still have plenty of motivation and ideas for this project, and now that the base Raycaster is set up, I can't wait to start bending reality. But this project has dragged on for way too long as it is, a couple of months in fact, so let's cork it here for now.
Honestly, my only regret is I never found a good use for this laser pointer. I can't even remember how to turn it on. Well, I guess this is my life now.
Hey, thanks for making it to the end of the video. If you enjoyed, make sure to like, subscribe, and I guess I'm supposed to tell you to ring that bell, but I never do, so I'm not gonna tell you that. Even though I kind of already did. Maybe I should have rehearsed that better. Anyways, in this post-video ramble, I wanted to talk about the video itself, and why it took over 2 months to release. The main reason is I was spending a lot of time trying to find my style, and to an extent myself. I had a version of this video that was a lot more animation heavy, including this scrapped avatar you're seeing now. It even had a fun robot voice, but in the end I decided not to use it. It was closer to what I wanted, but what I realized I wanted in the end was just to appear as myself, hence I added some skits to the video. The final product has a lot of different styles in it, including screen recordings, animations, the live skits, stock footage, and even some pen and paper scenes I ended up scrapping. As for the animations themselves, I'm actually quite proud of them. They're definitely nothing groundbreaking, but a lot better than I expected to be able to do myself. I also thought I only needed like 5 or 10 for the video, but ended up with over 30, so yeah, that took a while. And in the end, I realized I kinda had it all backwards. I thought I needed to know my style to be creative, but it's not that way at all, it's the opposite. Having a style isn't a prerequisite to being creative, it's actually the reward. You find your style through being creative. And even then, it's not really a journey you finish, it's more of like a horizon to strive for. Your style's always improving, you're always improving, changing, and I think that's what I'm going to do going forwards. You might see the style more often, you might not, I don't know, whatever I feel like doing for the specific video. But the point is, I enjoy making it, and I think that's what matters. Anyways, thanks for making it to the end, and hopefully my next video won't take 2 months, but I wouldn't hold my breath. Anyway, thanks again, and I'll catch you in the next one. Take care, guys.